Hi, my name is Junji and this is Lucy, and today we are bringing you a part of what we do in the Department of Chemistry at Iowa State University, where we try to invent new ways to make molecules. So I am an assistant professor in the Department of Chemistry, and this is my student Lucy. Today we are going to show you a little bit about what we do, how we think about phenomena around us as chemists.
Mm-hmm. Yep.
All right.
Okay. All right. So yeah.
So we start with something that is a little bit familiar to us. So this is spinach. I think we all eat spinach. You can think, even within this simple vegetable, we think of it as a homogeneous material. It is in fact made up of numerous chemicals, and every single plant produces many chemicals. And part of our daily lives is about separating these chemicals so that we can study them and find out how they contribute to our nutrition. So Lucy is going to show us a process in which we can separate the components of spinach into its various chemicals.
Mm-hmm.
So
okay. So just this is what we're starting with. So this is called, what we're doing today is called thin layer chromatography, just a method of separating out like the various like compounds, as Junji said. So if you notice, like at the very beginning, we're gonna start with like just a solid like green line. And then we're gonna see like what happens as the TLC plate develops. So the plate that I have is very polar. You guys might be familiar with like polar versus non-polar compounds. Like an example is like water is a very polar compound. And so the plate that I have it on, the compound spread on, is very polar. And I'm putting it into some solvent, just some liquid solvent that is more non-polar. And so how that works is some of the compounds are going to be more attracted to the silica plate versus other ones are going to be more attracted to the solvent, and they're going to travel up this plate and separate into individual bands. So this is going to take a little bit to develop. So we're going to move on to our next demo as we let that go, and then we'll come back to it and show you guys what happens. Okay.
So electrolysis.
Yep.
All right. So a big part of what we do is also thinking about chemical reactions and what the individual molecules are made up of simpler atoms. So something that we look at every day is water. Water, as all we would know, would be abbreviated or written as H2O in chemical formula. And H2O has two different elements, hydrogen and oxygen. And as chemists, we kind of think about how we could convert them or how we could observe them in the pure elemental form. And in this experiment, we could try to supply some energy to water and break it down into oxygen, which is a gas. And on the other end of the electrical current, we can see hydrogen, where hydrogen is being produced. So this at one end, at one terminus of, say, like this large battery that you're going to see, is that it produces 4 electrons in this process, and these same 4 electrons are then supplied to the other terminus of the battery, which then uses it to make hydrogen gas. So for a successful reaction, we will anticipate that we will make 2 different types of gases, oxygen and hydrogen. And importantly, this is going to be a 1:2 ratio. So that's the first observation. So the second observation that we will anticipate for a successful reaction is that this produces hydroxide, which then increases the pH. So we have a pH indicator that is in our setup. And we should see certain changes with regards to pH. So we should observe some color change. And we should produce gases in a 1:2 ratio. So Lucy is going to talk us through the setup.
Yeah. All right. So right here we have just like a really large battery, and so that's what's going to supply us with the energy to actually make the electrolysis happen. So in this tube, like Junchi said, so we have an indicator, and we also have a solution that's going to allow like the electrons to pass between like the two reactions as they're occurring like simultaneously. And these two, so we have like these two are stoppered, so that we'll be able to see the production of gas, and we'll let it go for a little bit longer, so that we're able to see the very obvious like 1:2 ratio. So I'm going to go ahead and turn this on, and right away, so then I'm going to crank up the voltage. And right away, we already see like the production of some gases forming here. And you'll also notice on this side, now we're also starting to see a color change. So that it begins like quite rapidly, but the effect of letting it sit for a little bit longer is very interesting to see.
Mm-hmm. We'll go ahead and mark the starting point.
Yeah. All right, so this will allow us to really monitor that change and see the ratio between the two gases that are forming.
Okay.
Okay. So another one that we've got to wait on for a little bit.
Well, we'll let that go. And then in the meantime, I'm going to take you to another chemical reaction in which very often in everyday life, everything is in equilibrium. So, which means that reactions are going forward, and also reactions are also going backward. And we can control whether the reaction goes forward or backward by certain parameters such as temperature, or putting in more building blocks that make one compound over the other. So in this experiment, we'll see two different species, and Lucy is going to show you the two different types of compounds that we have. One that is colored blue and one is colored pink.
Okay. So these three flasks that we have like prepared already, you'll notice they're kind of a purple color. So they're right now like at a perfect equilibrium between like the blue complex and the pink complex. So the first experiment that we're going to show you to manipulate that equilibrium is we're going to put one in hot water, and we'll just let that sit for a second, and then I'm going to put the other one in some dry ice. And we're going to leave one there as just sort of a control. Add a little bit more dry ice to this. Okay. So while that one's cooling down, we can already come back over here. All right. So now we do see, so the bottom is still a little bit purple, so I think we should let it sit for a little bit longer.
It's
getting close. But you can already kind of start to see that change into the blue complex.
Mm-hmm. And that is because at different temperatures, the stability of each of these complexes are different. So at high temperature, this is favored, this is more stable. So the pink slowly gets converted into the blue complex. And at lower temperatures, as you will see later, the blue complex then slowly starts to turn pink. So temperature is something that we could easily control, say, by heating or cooling to get a certain compound that we want. How's that looking?
It close. It is.
You see that it's a little bit more pink.
It's a little bit more pink. So
and the control experiment where we leave it at room temperature.
So the cooling is a little bit more difficult just because of the method of cooling that we have to do, but you guys will see in the next step for this, we'll get that really clear like pink color.
So
okay.
All right, so we are going to start with this blue complex, and we'll show you that by putting in more of the pink building blocks, we are able to shift this. As we put more of this, we will be able to move this forward into the pink complex, and we can approach this from two different angles. So either we start with the blue, or we can start with the pink, and shift the reaction that way.
Okay. All right. So we'll start with pink. Okay. All right, so again, we kind of have that equilibrium, the purple color. And what I'm adding right now is water. So water is one of those building blocks that Junchi was talking about.
It is the square building block. And as you add more and more water, you get more and more pink color.
All right, so that's a nice pink color. So compared to our equilibrium starting, so now it's shifted towards pink. But we can still go back the other way by adding some of the other building block.
So now we're adding more of the blue one, and we are going to shift it back here. So you can already see that the two layers, with the top one being more and more blue.
All right.
So those are the two ways that you can control what we want out of a chemical reaction. Either getting to the blue or the pink by controlling what we put into the reaction, and also by temperature, by either heating it or cooling it.
Yep. And you can see it takes a little bit of time for them to kind of go back to their equilibrium color as well. So the cold one is even still pretty pink, and the warm one was still pretty blue. We want to try one more time to go back to pink?
Sure.
Okay.
We'll try.
Yeah. I think the pink one was easier.
Pink one is easier. There we go.
All right. Yeah.
Okay.
Cool.
Do we want to take a look at the electrolysis or the spinach?
So let's go, we'll give the spinach another couple minutes. Let's go back to the electrolysis first. Okay. Oh, grab the marker. All right. All right, so we can see, I'll mark it here just so that it's really, really clear, the liquid levels. So we have almost like perfectly like a 2-to-1 ratio between the two gases that were formed. So if we didn't know anything like about this setup, like which one was actually at the cathode or the anode, we would actually be able to decide that this side, the one that is connected to the cathode actually is the red one, is in fact like because the oxygen was produced on this side. And so this is our 1 and then to 2 ratio, so the hydrogen is on this side. And then we can also tell, based on our indicator, that this side is the one that is acidic, as it turned yellow with the indicator, and then the other side is basic. And you can see the gas is still forming like pretty rapidly as the lines
we
that I
speak.
marked are already off again. Yeah.
So, cool.
Yeah.
So we do indeed have a successful reaction as indicated by the observations that we make on the reaction setup.
And so another interesting thing too is that so if we shut off our voltage and recombine this solution, it's automatically going to go back to the green color that we started with. So if we just give it a second to mix, so you can see it's already going back. So it's not a permanent
Right.
thing.
And we also anticipate this because it is a combination of acid and base, which then neutralizes each other. And then that goes back to our original green solution as what we have over here. All right.
Okay.
All right.
So
How's our spinach looking?
it's looking pretty good. We got some separation.
Okay, we got separation.
All right. So I'll go ahead and take this plate out now. Okay. All right, so it's still pretty wet, so it's a little difficult to see the clear separation of some of the lines. But if we look up here, so we know we started with like a solid green line at the bottom.
Crushed spinach.
Yep, crushed spinach. So I had the spinach, I ground it all up, extracted that with like some organic solvent, and then use that to make the green line, the solid green line on the bottom. So now as you can see, so we've got a yellow line at the top, and then like a dark blue. We do have a green line still, another yellow line. So as we can see, like this spinach is actually very complex. It's not just made up of one thing. There are multiple components.
And the ones that we are seeing are only the ones that produce color. And in nature, there are many, many compounds that do not produce color. And we'll need other forms of detection to actually be able to look at it. But even for the color compounds, green is just not just green itself. There is yellow, and there's some brown, and there's also some green. And they are clearly very chemically different from each other because they have different polarities, as Lucy has mentioned.
Yeah.
Okay. So moving on to our next demonstration. We actually need water.
Okay. I'm gonna get the put this on.
Well, you
Pour
want
some in there.
Okay. Let me change this up.
Okay. So you need a little bit of a swap out for this next one. Okay.
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 We are going to do this. The genie in the bottle. Okay.
Yep.
So we are going to put some water in the cans, and we are going to do an experiment with water and cans, and we show you how some of the destructive forces in nature come about in this experiment. So while that is heating up the water, we are going to go ahead with some of the chemistry that we look at every day, that is all around us every day. So we're going to start with some of the. So we're going to talk about mixing chemicals, first in a productive fashion, and then one in a really destructive fashion. So I think we are familiar with, say, bread and how how you observe certain bubbles in the bread. So for soda bread, a basic recipe for that would be your flour, baking soda, buttermilk, or if you don't have buttermilk, some recipes will ask you to mix milk and vinegar. And then, of course, for flavor, we want some salt in our bread. And the purpose of the two key ingredients in this mixture that will give us a good bread is the mixture of the baking soda and the buttermilk. So baking soda is something that we, as chemists, would call sodium bicarbonate, or sodium bicarb for short. And it is a base. And whenever you use baking soda, you want to make sure that you actually have a source of acid. And this source of acid is something that most of the time tastes sour. Say, for example, your buttermilk has a tinge of sourness in it. And that's because it contains some acid. Alright, and if you don't have buttermilk, then you can kind of make your own buttermilk by mixing milk and vinegar. Again, vinegar tastes sour, and then it contains something that we call acetic acid. And this is what happens when you mix sodium bicarbonate with an acid.
Alright. Okay. So we have sodium bicarbonate as our base. So I'm just going to put a little bit in that beaker. And then the acid that we're using today is citric acid. So this is an acid that is commonly found in like your fruit juices, so apple juice, orange juice. Those will both contain citric acid. We're going to prepare some cleanup materials. All right. So we're just going to add a little bit at a time. So if you can kind of see, so we're getting that bubbling, that foaming. Mm-hmm. So this is what is responsible for making those like nice, like fluffy air pockets in your bread, is that reaction of the acid and the base. So if this were the actual proportions in our bread, it would be a pretty fluffy bread.
It would be pretty fluffy bread. You'll get trapped by all the flour that is around it. So, and then you get a nice product. So if you get a very dense bread, perhaps think about sodium bicarbonate and a source of acid. And perhaps you either need more of one or the other. Mm-hmm. So this is one example of how we make use of chemistry to improve to incorporate chemistry into our daily lives. So the other chemical that you might have come across in your household is hydrogen peroxide. We use it for cleaning, or we use it as an antiseptic. You very often see that this has certain specifications, and you never want to use hydrogen peroxide in a metal pail. And we're going to show you potentially what could happen if you mix a lot of hydrogen peroxide with a lot of with some reactive metals.
All right. So here I have the hydrogen peroxide solution. And I'm just going to pour it into this bottle. And then I also have this little baggie, which contains a metal. So this is gonna give you a demonstration of like what would occur if you like accidentally had a hydrogen peroxide interacting with the metal. And it starts a little bit slow, but then it's actually pretty dramatic. Let's make sure we're not under. Okay, it's just not okay. There's a lot of steam produced, so it's nothing that's dangerous. But we just have to make sure that we don't set off the smoke alarms. But they should be turned off. Okay. So as the reaction's starting, you can see that steam building up inside the flask, and now it
gets dramatic.
Yep.
And this is something that we can't control. So it is, as chemists, we think about, okay, when should we mix chemicals and when we should not mix chemicals. Mm-hmm. So these are two chemicals that we never want to mix, hydrogen peroxide and a metal can. First, it will destroy the metal, and then second of all, destroys the properties of the hydrogen peroxide and changes that to water and oxygen, mm-hmm. which has no cleaning or antiseptic abilities. Mm-hmm.
And you can also tell, so like the flask is really, really hot. So this reaction releases a lot of energy as well. Mm-hmm. So if it's not contained properly, that can be another thing that can start maybe subsequent reactions that you don't want to happen. So it's always important to know what you're dealing with when you're handling chemicals and know what's incompatible.
Mm-hmm. Okay. Now I believe the water has heated up. Now I can see steam.
Okay, awesome.
And I can, yep.
All right. All right.
So we have water in a can. We heated it up. The water is now boiling. And we are going to plunge this.
Yep. So we'll show you first, and then Junchi will explain what's happening. All right.
Okay. We'll do another one.
We'll do another one.
Is there water in there?
Yeah, there's definitely water.
Yeah.
Okay. So sometimes that happens in science. Your experiments fail, but that's okay.
We gotta keep soldiering on.
Yep. And you also always set up a backup too.
Always have a plan B. Not working for us today.
Nope. Wow. It for sure was steaming. And there was water. Okay. So maybe we'll explain, and then we'll try and get these heated again.
All right. So water in a can. So this is our can. We put some water in there. And water itself, H2O. If we had zoom in, if we had a really great microscope, this will be what we see. Water molecules interacting with each other. Close together in the liquid. And so right up here where there is air, this is not an empty space, right? So this has air in there, and air contains nitrogen, oxygen, which we need to breathe, a little bit of carbon dioxide, and water plus other gases. So these are all occupying the space above the can. So when we heat it up, what happens is that these molecules, these air molecules, are going to start escaping into the atmosphere as the water molecules gain energy and transfer from the liquid phase to the gaseous phase. So when we heat up, some of the liquid will start escaping into the can, so the space above the water level. All right, whereas the air that was in there is now being forced out. Now what we anticipate is that if we are able to cool this rapidly and condense the water back into the aqueous phase or the liquid form, then we should be able to, what is going to happen is that, now when we invert this, if we are able to cool this down and then invert the can into, say, some water, and then be able to cool this rapidly down, then the water molecules are going to get rapidly transferred back into the liquid phase. And what's going to happen is that this space above the can is going to get empty. And what we have here is vacuum. And because the bottom part of it is sealed, air cannot go into the can. And when we have a vacuum and when we have atmosphere outside, the atmosphere, the air around us actually is able to crush the can. So that the crushing effect is what we are aiming for and we are hoping to see.
All right, there, it sounds like they're going, so give this another
Let's see if we can make it happen this time.
There we go. All right. There we go. So it's pretty, like, it's a pretty dramatic effect. Like there is a true vacuum in there, so the pressure of the air, we don't feel it naturally, but 1 atmosphere of pressure is actually pretty significant enough to crush a can like this.
And that's why we have a blood pressure that maintains us in our current shape. And when we go to outer space, the blood pressure that is meant to resist the crushing effect of the atmosphere will cause us to explode in outer space, where outer space is a vacuum. So the other way around. So this is an implosion, where the inner where the inner part of the can is a vacuum. So let's see
one more.
Again.
There we go. All right, cool.
All right. So that brings us to the end of our demonstrations. And
So today we hope that we have given you guys a taste of what it's like to see the world through the eyes of a chemist.
And we invite you to join us on our journey towards discovering more new reactions and new phenomena about us. So see you around and take care. Bye-bye.
Thank you.